So we left a bit of a cliffhanger last time.
You know what else we should do? We should share our screen.
We should share the screen. That's a very sensible thing to do. Share, or at least the Emacs buffer. Right. And then I want to hide the floating meeting control, except the menu moved and I clicked something random instead of what I wanted. It's funny when how that goes. Alrighty. So let's just try to remember where we got to last time. We were in the middle of proving that our test for the nullability of regular expressions was what it should do, right? So let's remember how we got there. We have Booleans, and we've got some standard issue Boolean operations like OR. And I've got this handy fact here, which says that if OR returns true, that must be because one of the bits was true. Yes, at least. And here's and then the same sort of deal, actually. If and returns true, that must mean both of the inputs were true. So we're just doing some little bit of joinery to connect Boolean logic with propositional logic. We also have this fact that when you have an equivalence, you certainly have an implication. So that's okay. And we've got lists, and we've got concatenation, and then two handy facts about concatenation, which are, if you know how to deploy them, how to not have a miserable time doing dislikes proofs. So the first fact says, if you concatenate two things together and nothing comes out, then nothing went in. Seems fair enough, I hope. This other handy fact comes up all the time if you think about what happens when you've got a regular expression, which is a sequence of symbols, or at least starting with a symbol. You'll find that you might discover that you've got some split between the front bit and the back bit, and you know that all together it's not empty. So Z's got to be somewhere, right? So either X's is empty and Z is at the start of Y's, or X's is not empty and Z is at the start of X's. So in the situation where you know X's is not empty, then you know, so if X's is X cons X's prime, then you know that X is Z. And another fact about the tail of the list, namely that X's prime, the rest of X's and Y's together make up Z's. So this is just the sort of stuff that happens. You end up with kind of lots of little bits of equations given to you, and you need to kind of put them together to get something useful out. So sometimes it's a good idea to step away and think, what handy fact would get me there, rather than just being in the wars all the time. Okay, so recapping, we got regular expressions, and they're parameterized over an alphabet, and we're always going to use ABC in practice, but we've got a regular expression called fail, which doesn't like anything, and a regular expression, we can do OR for regular expressions. So you got two ways to win there. There's a regular expression that is happy with nothing, right? So that's the kind of opposite of fail, right? Fail is angry with everything. Null is happy with nothing. Then we've got something that behaves a bit like multiplication, it says the whole thing matches if the front thing matches the first part of the input and the back thing matches the second part of the input. So it's sequencing. And then star is repetition. So 0 or more things which match this. All right. So we also wrote down some rules. And in the middle of rehearsal last night, Fred and I realized that the precise way we set it up was going to damage us. So we've sneakily changed the rules since last week. I'll show you in a moment. Okay, so everything's the same for the story so far. There is no rule that says fail likes anything. Right, that's how you make sure fail likes stuff. You just don't make a rule for it. We say null likes nil. We say sim A likes any list you like as long as it's singleton A. Then there are two ways to show that P or Q likes something. Either you show that P likes it or that Q likes it. Fine. And then P then Q likes some input if you can split it into a front part and a back part, with P liking the front and Q liking the back. Reasonable? Right. Now, here's the thing that's subtly different. So what about star? Well, we say star is willing to take 0 or more repetitions of stuff matching P, right? So we're saying that star P certainly is content with nothing. And what we did last time was we said star P likes anything you can split into a front part that P likes and a back part that that star P likes. And that is a perfectly correct thing to do, and we could cope with it if ask was slightly more cunning than ask currently is. But we had to fix it up very slightly. We haven't changed what star likes. All we've said is that if you are going to unroll it by one step, you've got to give me a thing that isn't empty. So, saying is that the sum case says star P likes a non-empty input if your first thing that matches P consumes at least the first thing in the input, right? So this is the situation. If P is nullable, if P likes nil, then you are free to construct derivations of star P liking something by hopping up and down on the spot, accepting nothing, and then another nothing, and then another nothing, and, you know, eventually maybe getting around to doing some work. So what we're saying is that if you're actually going to deliver one thing that P likes at the front of the input, it has to consume at least one symbol, right? You know, so the point is that star P only likes the input if it eventually consumes all the symbols anyway, and the only way it can consume the input is by feeding them to P. So we haven't actually thrown away anything we like here. But we've made sure that at every step some input is consumed, which is going to enable us to do induction, right? You know, so right.
And this also matches how we actually use these rules, right?
Yes.
If you wanted to match the empty list, you should have used the first rule.
Yes. Yeah. So yeah, we haven't thrown anything away. In fact, we've tidied things up sensibly. We've just thrown away a lot of degenerate behavior. So so that's cool. And we were astonished that when we reloaded the file, nothing broke. I mean, how often does that happen? Yes. Okay. What else have we got? The inevitable handy facts, which essentially allow you to get back around to using the equations you've got kicking around, which say essentially that that the likes relation respects equality. And of course it does. Everything does. it's kind of annoying to have to prove this, but there we are. Right. And then we were doing nullable. Right. So the idea of nullable is to test whether a regular expression accepts the empty input. And that's a thing we can tell just by looking at it. Oops. Now, I actually want to do a bit of big picture. Well, what we're aiming for down the line is a thing called, well, let's call it likes with a small l, which takes a regex ABC and a list of ABC and gives us a bit. We want to test whether a regular expression likes an input. We've defined some rules for that, but that allows us to find out or to prove that a regular expression likes an input, whereas the whole point is that we want the computer to do the work, right? My favorite kind of pornography is watching machines do work that I don't have to do anymore. So just, showing that this is the computer's job, not our job, is always really satisfying. So let's kick off how we would do it. Likes PXs, and then we're going to go inductively. Right, the way we're going to do it is by working our way along the input. And of course, right. So we're split into two problems. Does P like nil? And does P like something beginning with X? So we're hoping to look at both of those problems today. And we know, so the whole point is that the first of these questions is exactly what nullable answers. Does P like nil? This is going to be nullable P. Okay, so let's go back to nullable. And we kind of thought it through reasonably carefully. And I don't know if this operation rings any bells, but well, we'll get there. So what we're saying is, does fail like nil? Well, fail doesn't like anything, so no. Does null like nil? Yes, that's what null's for. Does something that wants a symbol like nil? No, it doesn't. P or Q likes nil if P likes nil or Q likes nil. And once again, P then Q likes nil if both pieces are nullable, right? And then because you're allowed with star to have 0 repetitions, star R does indeed like nil. So that was our definition. And then we were in the process of proving that our function is fit for purpose. So if P likes nil if and only if the nullable test says true. We did a bunch of the easy cases, and we were somewhere close to the end of one case of OR. I think we were about to deploy the induction hypothesis. But yeah, I mean, what did we? Yes, so we were basically using, crucially, this relationship between Boolean OR, right? So we've got something which does a bitwise test, nullable Q or nullable R, and we wanted to turn that into a logical OR so that we could split into two cases. But you can see that the proof both ways round is going to go see which one worked and do the same thing on the other side of the equal sign. You know, if it was the left one, go left. If it was the right one, go right. So that we knocked off. And I think we should warm up by doing star. Okay. So I don't think there's any choice but to just split it into both directions. And I can do one and you can do the other.
Yeah. Well, let's test it first, right?
Oh yeah, that's fair. We got to compute. Right. So we're hoping, this is why I said let's warm up on it. I don't know. I think cases deserve spaces. Right. So do we believe that star R likes nil? And do we believe I equals I? Right. Both of these things look pretty damn true to me. So okay. So one way round involves proving I equals I, and Ask is not bothered about that.
That's the direction you wanted me to do, right?
Yeah. So, and otherwise, we've got to prove that likes star R nil, and that would be by none. Okay, that was even easier than I remembered. Okay. So let's do the renaming dance. Right. Okay. So what's going to happen here? We know that let's just think about it for a bit first. That Q then R likes nil. We ought to be able to extract from that. That means you can chop nil up into two pieces, the front piece that Q likes and the back piece that R likes. And if you're chopping nil up, can you guess what the pieces are? I mean, so likewise, this nullable thing is we're doing a, well, let's do test, right? You will see any minute now. Why am I speculating? Right, you see we end up doing this Boolean and. Right. So at the moment, I know that when we take this thing apart, we'll get two possibilities. I also know that my induction hypothesis is going to tell me stuff about nullable Q being I or true and nullable R being true rather than this particular Boolean computation. So a very good start is to make use of this thing. So this is an equation. It's a logical equivalence, but you can still use all the bits and pieces that we have for reasoning with equations. So in particular, I'm going to say by root, and I'm going to pick this up, pop it down, and transform it into the logical counterpart. So we know that my root proposition, the one that I'm going to put in the middle, is equivalent to the thing on the right. So it's okay to put this in the middle. I'll get one sub-goal. And I do indeed. Okay. So now I don't think I've got any option but to just do it by equivalence and prove it both ways. Right. So what happens next? Which ones do you want to do?
Can I do the first one for a change?
Why not?
Right. Okay. So let's see. So we split it up in two ways and we can see what we want to do. So we are given that Q then R likes nil. And we want to prove these two facts, right? So there's basically two moves we can do at this point. So we are proving an AND. So we could do an AND introduction. Or we could look at how this is possible, right? By saying from this. And I think none of these options are wrong. It's just if I do the AND introduction now, then I'm going to end up looking at this in both branches, right? So I think it's a better move to do a from this thing first.
You betcha.
Say from this to see what the proof was.
Yeah.
And we see, well, the proof was because we could split up nil into these pieces, which I'm going to rename.
I also think cases deserve spaces. Why not separate the two halves of this equivalence by a little bit more?
Yes, I'll do that as soon as you tell me what to call these pieces.
I would call them X's and Y's. So,
X's and
we're on the blink on this one.
oh, okay. Well,
It was good while it lasted.
Indeed. Right. So,
maybe I'll see if it will respond to the document camera.
Right.
Like this.
Meanwhile, I messed up this. So these are our cases, right? Yep. Okay. So we know that nil is made up from X's and Y's, and we know that Q like X's and R like Y's, right? And as Connor was saying before, if nil is made up of two pieces, then we would really expect these pieces to be nil, right? There's no way something non-nil can make up nil. So do we have this fact?
Yeah, we do.
So let's see if we can find it. Right, so we have this thing here, right? Which says exactly what we expected, that if two things make up nil, then the two things are actually nil themselves, right? Okay, so let's see if we can deploy that. So I'm going to say from this.
Wasn't it fortunate that we called them X's and Y's?
And I guess I just deploy it like this and see
Yeah.
what happens. So, okay. So what happened was Ast went looking for a proof of this, but we have that given. So we just given the conclusion of this fact because this was a proven fact we had before, right? So that looks good, except this is an AND. So I'm just going to split this up into, if I could copy it. So I'll just split it up into the two individual facts. So now I know X's is nil and I know Y's is nil. And I know that X's likes, Q likes X's, and I look that R likes Y's, but they are nil. So by the induction hypothesis, I should know that Q is nullable and that R is nullable, which is what I wanted, right? So I think yep.
So what now we're playing the game of swearing, because the place we would like to rewrite, the things we would like to rewrite are already in the givens rather than in the goal. So we need to think about how to get our hands on them.
So I think step one now is in any case to do an and introduction, right? I want to prove these two things, and I just have to do them one by one.
Yeah. Actually, well, okay. I'm having a thought, but
yeah. So let's see. So what we would like to say is the induction hypothesis, right? So likes Q nil implies nullable Q is 1. But what we could say, so the induction hypothesis, unfortunately, says likes Q nil is equal to nullable Q.
yeah.
Yes,
and then you got that.
So then I can, but we have this fact that if two propositions are equal, and I know the first one, then that implies the second one, right?
Right.
So that doesn't work. Why does that not work?
Oh, brackets.
Ah.
You need an extra set of brackets around the right equation. Nullable Q equals I.
Ah.
Yeah, it doesn't know which equal sign is the outermost one.
Right.
No, not that one.
Uh-huh.
The one in the equation. You've got A equals B equals C.
Right, this one.
That one. Yes.
Uh-huh. Okay. Yes, that makes sense to me as well.
Right.
Uh-huh. Okay. So now ask says, okay, you claim that this thing implies the thing you want. It agrees. So now all we have to do is to prove the hypothesis of this thing, which is another and. So we can do that by and introduction. And we already know the first fact by the induction hypothesis. So that's good. But why is it the case that Q likes nil? Well, it should be the case because Q likes excess and x is equal to nil, right? So we had another one of these boring facts that says that, well, if Q likes something and that thing is equal to something else, then Q also likes the something else, right? So if likes Q excess and excess is nil, then likes Q nil, right? Okay, and then we're in the same situation again, where we have to prove the assumption of this little implication. And it's an and, so we do it by and introduction. And this time, both cases are obvious from the context we have. So we know that Q likes excess. That was this given assumption here. And we know that excess is nil. That was this given assumption here. So there's nothing to prove, right?
Copy, paste, search for place.
Because now we want to do exactly the same thing, but with R, right? So do we dare to do this? So
yeah, R and Y's.
Copy this. I paste it in, and then in here, I want to replace. Is this the meta button? No. Right. Might have to get you to do the search and replace on your keyboard.
I don't know how to do it.
Okay, fine. We'll do it by hand.
Yeah. Well, meta percent, escape percent.
Escape percent.
Yes.
Right. Right. So we said replace
X to Y's, that's handy.
X's to Y's, okay. So yes, 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 yes. And we are replacing Q by R, right?
Yeah.
Yes. Okay. So same proof. Let's send it to ask, and it is happy. Okay. So that was one direction. Not too much interesting was happening because we've already done the move of splitting up the and of the nullables, right? Let's see what happens the other way around.
Okay. Let's see what we can manage here. Right. Well, brain switched off. I've got a given and. I would rather have those two as separate pieces. So I'll do from on this thing. Okay. So now this is good because I ought to be able to get that Q likes nil and R likes nil from the induction hypotheses. And that's excellent news because, okay, I need to prove that Q then R likes nil. So I've got to come up with a way to split nil up into two pieces, a piece that Q likes and a piece that R likes. And, you know, it's really getting away from me. Split nil, nil. Okay, so now we have to show that Q likes nil. Fine. That's going to be from, now I have to do it this way around, and I have to put brackets in the right place. I mean, I could give myself two handy lemmas and save myself the trouble. Right, what I do is I write the equation down, and then I copy the equation, carefully leaving the brackets behind, paste it here, and then I stick an and in there, and I turn the equals into an arrow. That's the fact. I'm turning an equation into an implication. Okay, and that gets me there. I just have to prove the two antecedents, and that's, no, I don't want to spend money on and introduction. And we're done. Okay. So I'm gonna pick this up, put it there, and I think I'm just gonna, I should have highlighted the region, but it's not a big deal. Right. And there we are. All green on nullable. And you know, that's a non-trivial thing. I'm just looking at the time and thinking there is some stuff that I want to say about this program in the first place. Right, because once upon a time, we had a type of that we called formula, which had a notion of, which had formulae had one variable in, and they had numerical constants, and they had adding and multiplying. And we wrote a function called evaluate, which actually turned the formula into a piece of honest-to-goodness arithmetic. And what are we doing here? We are effectively seeing what this formula computes to. We're translating a regular expression to a Boolean, interpreting all of the symbols as falsity. So that's to say, we're saying, if you're not allowed any symbols, what to what does this regular expression evaluate? So it's a bit like, actually just shoving in 0 for all of the symbols and seeing what comes out. And so this is very, very similar to that evaluate operation, and all sorts of other things we've done, kind of transforming, in this case, like, one rig structure to another. So that's why I can be bothered to tell you about rig structures, is so that you know one when you see one, and you get suspicious when you're not mapping the ore to the ore, as it were. So that's pretty cool. And I guess we've still got quite a bit of time before the half-time break, so we should set up what's going on for the other part of this. Or actually, we could get ourselves some handy equipment. Right.
It's maybe worth pointing out as well that the proof he just did really says that his first line of lowercase likes is doing the right thing, right? But really, if it gets an input of nil, then it will return true if and only if he actually likes it.
Yeah, well, indeed, we want to prove that likes p x's is equivalent to likes p x's says true, right? That's what we want to do. We're gonna. So maybe this is a good thing to do before the halftime break, is get this proof underway, and then I know that I'm going to want to prove each direction separately. Or am I?
Actually, because
No.
the way we set up nullable,
It's not crazy. Let's
we don't even want the equivalence.
so let's go inductively on the input from x's. And hilariously, we only get the step case because the base case is true. Right? That's what we just did. Let's call this thing x. And I think this should be called x's prime. Right.
At which point it would be kind to rename the other x's to x's prime.
Which one?
The one in the definition of lowercase likes.
Okay, sure. Right. So we haven't said what to do yet, but there's only one game in town, which is like somehow we're trying to figure out whether P likes something beginning with X. And we know because we're inductively, right, okay, we're working our way along the input. Because why are we working our way along on the input, not working our way through the regular expression? Well, it's partly that we know we're going to have to use the same, if we get a star, we're going to have to use the same regular expression over and over again. And it's going to be the input that gets smaller as we work our way along it. So that's why it's a sensible thing to do. Right. So then the puzzle here is to figure out, we're going to be able to test x's prime, but we don't yet know what regular expression, or indeed if there is a regular expression, we would like to test x's prime with. So what we're interested in asking is, well, if P likes something that starts with X, what's the rest of the thing that starts with X going to be like? One thing's for sure, and I think this will get us to half time, is that we are going to need to be able to test equality of symbols. So, you know, suppose our regular expression here is, suppose P is you know, symbol A, or you know, some other symbol. We need to check, well, is the X in the input the symbol we're looking for? Because if it is, we're happy, and if it's not, we're sad. So one piece of equipment that we don't have for nothing is something that takes two ABCs and gives you a bit. And so we want to do this thing. And I'm afraid there's nothing for it in ask but to split this problem into 9 cases. It's going to be, so woohoo. But, you know, it's reassuringly boring, and then we have to get it right. So that's true, false, 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 true, false, false, oop,
Half zeros.
false, oop.
You have the same thing on the line above.
DC. Yes. False, false, true. Okay. But it's one of those things. Spend your life writing computer programs that test things, that compute a 0 or a 1. And you find that if you're lucky, there's some comments in your code that tells you what useful information that bit is telling you, right? Whereas the truth is that all that happens when you test something is you get a bit, right? Bit is useless unless you've got some important fact like prove ABC eq XY is true is equivalent to X actually being Y, right? So let's at least start this. What's going to happen is we're going to start this and it's going to be very, very boring. So we'll finish it during half time. In fact, we'll copy and paste it from our rehearsal file at half time. But yeah, here we go. We got a case where X is A and same deal. Can't type today.
So because ABCX was really looking at all the 9 cases, we have no choice here but to look at all the 9 cases again, right?
Yeah. And then we do things like test, right? And then we get, oh, a boring equation is equivalent to another boring equation. So, fortunately, that way round, we're done. This way round, and I must get around to fixing this. You say by equivalent, you can see that both sides of the equivalence are false, but you're still forced to point it out, right? From that from, right, you can see we're going to win, but it's not going to be very exciting. So is this a good point to call halftime?
I mean, you could maybe even see how to write a program that would write these proofs for you.
Yes. Yeah, we will we'll get on with this in the next hour with a bit of Polish magic. And that was the thing. We're going to show you a program that well, the question is, was it written in 1964 or 1764? 1664 even. Yes, so we're going to show you a program that was written by a Polish mathematician called Brzozowski, except arguably it was actually written by Isaac Newton. And it may ring bells. You never know. The message of CS103, as I cook it, is that there really aren't very many ideas. So let's, how do I do this? I hit home the recording and let's see if we can get back in the zone. So, you know, yes, indeed, we just did. We had a dip into our rehearsal file and grabbed the whole of this thoroughly unremarkable proof. Let's do something more exciting. Right. So we're going to define an operation called Brzo, after the person who invented it. And we've got to decide which way around to do it. I'm going to put the regex first today. So it takes a regex with symbols from ABC and a single symbol. And the question is, we want to give back another regex. So it's not obvious that this thing necessarily exists. The idea is that the regex we give back should be what has to like the rest of the input if we're gonna like the whole thing once we've seen the first symbol. I mean, that was word salad. So we're going to define this thing, right? And then let's set it up. So here, what's going to happen is that we're simply going to say, right, I'm going to write a question mark, right? You know, what has to like x's prime if P is going to like x cons x's prime? Well, this is exactly going to be Brzo Px. That's the plan. So we just have to figure out what's going to fit that plan. Okay. And that means we're going to have to prove that if likes P x cons x's prime, that is equivalent to likes Brzo Px x's prime. There we are. Replace word salad by logic you can read. That's the mission. And indeed, we ought to be able to finish this proof just given this thing. And maybe we should even do that first. Right. So right. What do we want to do? We want to go, we know, we see this thing here. And we see we've got we know an equation about it. And what's more, we would quite like to line something up for the induction hypothesis. So I'm going to say by root and give the other side of the equation. And then let's see where that gets us. Okay, no sub-goals, but still not done because we haven't proven this yet. Okay, so this gadget is fit for purpose. Let's get on and do it. Right. We're going to go inductively on P from P. And let's do these things in random order. Let's do symbol first, because that's kind of where we were going. Our regular expression will be happy if we give it an X and only an X. We're giving it a Y. So we know how to test whether X and Y are the same. If X and Y are different, we have had it. There is nothing you could put after the Y to make up for the fact that we wanted an X. We are angry with everything. Meanwhile, if X and Y are equal, we have got the X we were looking for, and we don't want anything more. So we will be happy with nothing, and indeed only with nothing. And this is exactly where we want to use our ensure gadget, which I can't remember if we've got. Have we got it?
Probably not.
Okay. Well, let's just do it again. So that was our thing, which basically says how to translate logical conditions into regular expressions. Where we said if the condition fails, we're angry with everything. If the condition it succeeds, then we don't want to consume any data, but we're happy. Okay. And now what on earth? Oh, it's because of my equal sign. Right. So what we want to say is ensure ABC equals. This was a program by Leopold Kronecker. Yes. Okay. So that's a nice one. Right. Terrible name choices. Well, actually, this is X. Maybe I should have called that one X and that one Y. Done it this way round, not that it matters. Right, so that's going to be Q and that's going to be R. Right. So Q or R, does it like things that begin with X? And if so, what's the rest of it? Wow. There's two ways Q or R could like something beginning with X. Q could like something beginning with X, in which case we better have the rest of the Q. Or R could like something beginning with X, in which case we'd better have the rest of the R. Never seen anything like that. Right. Do you want to knock off the easy ones?
Yep.
And then we can take turns on the tricky one.
Right, so let's think about fail and null, because these are the easy ones, right? Let's maybe start with null. So what should we put after? So this should be something that is happy to accept x cons x's if null likes x's, right?
Oh, yeah.
Other way around. It should be something that likes x cons x's if null likes x's.
Yes. How do we keep going if we want null to like something beginning with X?
Yeah. So null doesn't like anything beginning with x, right? So this is just forced to be fail, right? If we look,
Okay. So yeah, we've just died. We've run out of input when we wanted an X.
we look down here, we want the thing we're defining here to like x's prime if null likes this non-nil thing. Null never likes this non-nil thing, so this should never succeed, and that's exactly what fail is doing, right? Okay, so that one's defined. What about this one? So we look down here again. So we want something that likes x's prime if fail likes x cons x's prime. But again, fail will never like anything. So this right-hand side should also never like anything, right? So this should also be fail.
If we were dead already, we stay dead. Okay. Let's do star next. Right. So, under what circumstances would star of R like something beginning with X? Wow. Star of R is happy with nothing, but that's not what could possibly be going on if they're actually consuming at least one X. So that means there must be at least one R on the front of whatever this thing likes. And that has to begin with an X. So this had better be, we better start with, so the rest of the input better start with the rest of the first R after the X. But there might be more R's, 0 or more of them. So we better stick a star R on the end. So we kind of say, there's got to be at least one. We've taken a bite of it. We're asking for the rest of it. And then we're asking for some more. Make sense? Okay. So now This is this story so far ringing any bells with anyone? Right, sort of all the constants end up turning into zero. The thing that behaves like or just preserves everything. The thing that the thing that behaves a bit like variables turns to zero if it's not the variable you're looking for, and one if it is the variable you're looking for, and then you know, something funny's going on.
I think we should do this one and then come back to it.
Yes, but I'm just trying to encourage you to search through bits of mathematics you may have learned once upon a time, and check for any passing resemblances. Okay. So, how could Q then R begin with X? Now we're allowed to ask, well, what about Q? What about R? But we also have to remember that this X comes first. So I can see two possibilities. Either the Q gets the X or the R gets the X. So let's figure out what happens. So what's going to happen is there's going to be an equal sign. And I'm going to write this like that. As I know that line above is going to become one character longer. Okay. So let's deal with the case where the Q gets the X. So we're going to start with the rest of the Q after the X. So what happens to the R? Right. We haven't got there yet. We're still somewhere in the middle of the Q. So to make up the whole of a Q then R, we have to leave the R alone. Meanwhile, there's if the R is getting the X, we're going to have to finish off. So we're going to have to say, please give me the rest of the R after the X. But if it's the R getting the X, what must have been true about Q? Remember, the X comes first. Right?
So the Q can't consume anything in this case, right?
Yeah. The Q must have taken nothing, which is possible if the Q is nullable.
And conversely, if Q is not nullable, then this path will just fail, right? Because then Q will be forced to consume the X, and the R can't get the X anymore because it's already been consumed. Right? So this ensure really does the right thing. If Q is nullable, then we should be happy and not consume anything. If Q is not nullable, then we should just fail, right?
So that's our definition. And maybe I'll even sugar that along to there. This It's sort of like some things you've seen. It's sort of like, but it's not quite. If you think of then as a funny kind of multiplication and or as a funny kind of plus, it's got a flavor to it, has this operation. And so it's not doing the derivative you learned in high school, just as the forward difference operator we had last semester was not doing exactly the infinitesimal derivative you learned in high school. But this is yet another differential operator known as Brzozowski's derivative. And it's another instance of a more generic notion that Isaac Newton worked with called the divided difference, right? So where you compute a slope of a curve, you know, you do compute f of y minus f of x divided by y minus x, right? And then the deal is what happens, you get different differential operators depending on whether you say, oh, let x and y tend to be the same thing, or let them be one apart, or whatever it happens to be. But they're all instances of that general scheme. This is yet another one. And it's really about what we're saying is, can we put our finger on a leftmost x? And the case for then is saying either our finger goes in the Q or there was nothing in the Q and our finger goes in the R. So these differential operators, they're all about some kind of pointing. That's the important thing for computer scientists to know. Okay. Shall we do this proof? I think it does work better if you split it up as as two separate cases. Oh dear. Should either paint my fingernails or cut them. Right. So the plan is that we're going to farm these out as separate proof obligations because they will work more easily that way. Like that, question mark, and then this is going to be from that away. So again, we haven't gone green, but we've got no sub goals from that away. Right, so now we've got two individual proofs, and I think we should do them both at the same time.
Yeah.
And deal with one regular expression component at a time. So, so this is going to go inductively on P, because that's what Brzozowski does. So inductively P from P, yuck. Inductively P from P. Right. Horrid choices of names. So, okay, next up, it's always going to be tests and then implication introduction, isn't it? Right. Test. and by imp I'm just picking an easy one, but you can pick an easy one next as well. Right, okay, and then we've got fail likes something. I don't think you do. And then here, test. We've got fail like something.
Yeah, in the section. Yeah.
Yes. And then oop. I don't think you do. Right. And then I should follow my own dictum that cases deserve spaces and invite Fred to pick the next one from this week's show.
Okay, so let's do the null case, right? And again, there is not too much to do to start with. We are trying to prove an implication, or maybe we do the test first.
Yeah,
so we have some computation that could happen here, right? Because we have defined Brzozowski null to be something. So we say test. Then we say, well, that has become fail. And now I'll do the implication. So I'm given that null likes this non-empty list. That's a bit suspicious. And I have to prove this impossible thing, right? So I have no hope of actually proving this. So my only hope is that this is impossible. So I'll just say, what could this proof possibly be? Say, from this. And actually, it couldn't have been anything. So that gets me out of trouble, right? And down here, in the other direction, again, we have some computation that could happen. So I'll start by saying test. Well, that computed to fail. Implication introduction. And now I've been given that fail likes something, but I know fail doesn't like anything. So I'm going to see where that came from. And it couldn't have been anything. So actually, this is also okay, right? Okay, should I do one more? Why don't you do one?
I'll do, well, okay. Sooner or later, we're going to have to do the nasty one. So let's make it sooner. So here, let's look at the case where our formula is sim y. And then I'm gonna worry. Right. So what happened there, right? We've computed to ensure. Okay. So what happens? Well, implication introduction happens. And then I've got some stuff, right? I've got a handy fact. There's only one way this liking could have happened. So let's unpack that. Okay. And then there's only one way that equation can be true. Which is if the pieces line up. Okay. So that's good. So I'm going to just say from x is prime equals nil. And I think I might even, although it's not strictly necessary, turn that x into a y. Okay. So now we've got to do something with that thing. Well, we know whatever y is, a, b, c, eq, y, y is going to turn out to be true, and that's going to turn our thing into that's going to mean we end up with null, which is great news. So I'm just trying to decide how to do this, and I'm minded to do it by brute force and ignorance. So, right, there's a time and a place for why is it stuck, right? We know why this hasn't computed to null already. It's that we don't know what y is. So let's just from it to death. And then I know it's boring. Well, actually, can I just say by done? No, it's by, yeah, it is by done. Does that work? Yeah. So let's just skip the test and make ask do it. Right. So that was the easy way around. Same thing down here, only the other way up. Right, 757 better be y. And what happens? Right, test is what happens. Okay, so we need to know what happens, and there's two possibilities. Either the equality test says they're equal, or the equality test says they're not. And our strategy for these two things is going to be rather different. So I think I'm going to prove a handy fact, the Boolean law of the excluded middle.
Actually, you have proven it up there already.
Have I? Oh, I have. Oh, that's nice. It's almost as if some of this stuff happened in rehearsal. Yes. So here, there's you know, there's no three ways about it. If you've got a bit, it has to be a 0 or a 1. Fine. So there is a bit I'm very much interested in. Right. So that ought to be useful information somewhere along the line. So now we go by implication introduction. Right. And we can at least see what game we're playing. We want to be able to extract a proof of we see that this actually computes false. So we know that we're hoping to refute this given. So that's nice. What am I going to do? Well, I'm going to use the fact that so if I knew this thing, and that this thing is equal to fail, then I would know likes fail x is prime. So I know morally that's how it's going to end up, is that we're going to need to use that fact. So it's asking me to say, well, pony up the inputs to that implication and then show that the outputs get you home. So let's do the latter first. From that thing. Okay. And now I've got to do and introduction to get the two pieces separately. And I'm hoping that the one on the left is going away. I've still got a bit of work to do on the right. And here's a standard piece of ask horridness. We really want to turn this into the false that we know it is. So we know that, in fact, this fail is really ensure of false. And then that will work out, if I say under ensure, that will reduce to the equation that we know. Thank goodness for that. Okay. So now what about the other game where the x and y are equal? We've got to now we know we're gonna need to make sure that we have that fact. And we are going to want two things here. We are going to want y to be x, and we're going to want x's prime to be nil. So we're really going to need to use the fact that this is going to turn into null. That's what's going to get us that x's prime is nil. So we would really like just about now to have a logical equation, y equals x, rather than that a test has happened. So I'm going to say that's from this thing is equivalent to y equals x, being very careful about the brackets because we've got three equal signs. So that's that equation. And the left-hand side implies the right-hand side. So that's a fact we know. And then I have to prove that, but that's going to be by and introduction. That's fine. Okay, now I've got that y equals x. Excellent stuff. From y equals x. Right. Now what happens? Well, I think I have to do implication introduction because I'm going to have to do another maneuver where I use the fact that I know an equation. So implication introduction gets me an assumption in the right place. And then I'm going to say, well, I know this thing. And that this thing is null, and I would like to be rewarded by like null x's prime. Likes, yes. All righty. So let's do the second thing first, because that's the meat of the argument. We would really like x's prime to be the empty list, and we've got a pretty good clue about that. Right. So now we're asking, does sim x like singleton x? And that's by exact. And now we're left knocking this thing off. We expect the left subgoal to go away. And now we have to do to show that this equation holds. But now I might have painted myself into a corner. Yeah.
That bad?
It's annoying.
Do the same move again.
I can do almost the same move again, but the trouble is that the assumption that I've got talks about y. So I will clean this up later.
Right, but you can just do a from on x. That should always compute to true anyway.
Yes, that's true. Let's just do it by brute force and ignorance.
But I wonder
Okay. So that could have been a lot worse. Right. So we've got our three base cases done. It's 10:43. So let's do or because it's boring. You know what's happening, don't you? You know the and star are going to be homework. And I'll give you a clue. Star is really easy. And is a bit of a fiddle. But why don't you do or?
do or, okay.
Right, so let's rename these things. This is Q. This is R. Okay, and then let's see what we have. So the first thing we can do, we have this function that should compute a little bit more. So we'll test it. Okay, so it has just distributed the regex or okay. So I think I'll just do this by an imp introduction at this point. Except I can't. Yes. Okay, so we are assuming this and we want to prove this. But we have an assumption that a regex or likes something. And there's two ways that could happen, right? So let's do a from on that to see where it came from. Okay, so I'll do a from on that. And its line is a little bit long, so maybe I'll do that. Okay, and there was two cases. It was either because the left regex liked it or the right one did, right? So let's see. So here we have the left one. And I would like to show that an or likes something. So again, I do that by going left or going right, right? And I know something about the derivative of q. So I should probably go left here to do the q thing, right? So I'm going to say y go left. Okay, and then I have to show this. But then I see that this is exactly what I get from the induction hypothesis for q, right? I get to say from missing the L, okay. So this implies what I want. And that's it. And in the other case, it's going to be the same thing, right? But this time I'm going to go right. And I'll do the same thing.
Yes.
Except my Q's are R's.
Right.
Okay, so that wasn't too bad. But we should also do the other direction.
But you're not going to faint with amazement at how this works.
So let's rename. This is Q. This is R. Okay, and we're proving an implication. So we'll start by doing an
I
implication.
would do a test, to be honest.
Okay, you're right. So we have this function here that might compute a little bit more. And I'm not sure what happened to my cursor here. Yeah. Okay, so this thing has computed the same thing it computed to, right? Now I'm proving an implication, so I'm going to introduce my implication. And again, I have an assumption that an or likes something. So let's see in which way my or likes this list. Well, it was either because Q liked it or because R liked it. If Q likes it, then again, I'm going to go left because here I have something talking about Q. Now I need this. But again, this is the induction hypothesis, right? So from this, the bracket at the end. Get the thing I want. Okay. And again, this case is completely symmetrical, right? So now I know something about R. So I choose to go right because that's where we know things are asked to prove things about R. And then it's the same induction hypothesis thing, but with R. There we go. So that's straightforward because the definition of the function was very straightforward, right? It was just turning ors into ors, right? Whereas things get much more interesting for the and because they were actually doing something. Okay.
That's good news. The other two are more complicated than we can get done in 5 minutes. But we'll give you a go at them. But in any case, pick it up next week. But you can see what we're going for. We've actually got a sensible way of testing whether a regular expression actually matches an input just by working away one thing at a time, and it's hooked to a variation on the recipe of differentiation, what you learned in high school, what we did in semester 1. Calculus is really the thing that unlocks our whole world. So get hep to it. Also, it's what all the machine learning people do. So yeah. It's so okay, thanks for coming, and we'll get this video online real soon. And yeah, have a lovely weekend. See you next week.